Hello everyone, welcome to this session on dielectrics. This is one of the units as part of the engineering physics course. Now let's go to this notes which I already shared with you people. So these are my lecture notes and we start with obviously with the first question which comes into the mind is when you start a particular unit, what is that unit about? So this unit is about different types of dielectric materials. So what are these dielectric materials? They are insulators. They are basically insulators. That means there are no free charge carriers. So what does it refer to? If you all remember, an insulator will not have any kind of conduction electrons. All the electrons stay in the valence band, that means the valence electrons, and the energy gap between the valence band and the conduction band is too huge that these valence electrons are not able to go towards the conduction band. That means they are not free charge carriers. They cannot become free charge carriers. If that is the case, what is the use of an insulator or a dielectric? Being an insulator, what is the purpose it is going to serve for? Now here is the thing. Being placed in an electric field, these materials are going to undergo some changes and act as storage for electrical charges. In short, I will say that having a dielectric material within a capacitor is going to increase the total capacitance. How to understand this? Let's go down a bit and come to this figure over here where you see that I have represented two parallel plates of capacitor here, and if I apply a potential across these plates, I will get, say I have given positive potential to this plate and negative potential to this plate, I'll get positive free charges here and negative free charges. Now imagine the first case where you only have the parallel plates of capacitor. That's what you already seen earlier in your PU classes or your 12th standard. Now what we are going to do, so in that case when you had just the parallel plates, the medium in between was just the air. Now I am going to bring in a material, an insulating material called as a dielectric. I'm going to keep it over here. Now what is going to happen because of this dielectric? That's what we are going to learn in this particular session. Now you can see that when you applied potential to these parallel plates of the capacitor, initially it produced some charges, the free charges. The free charges will result into an electric field. That means because of the applied potential, an electric field is being generated between the parallel plates of the capacitor. So now when I keep this dielectric in between the parallel plates of the capacitor, this electric field, that is the field due to the free charges, that is going to act upon the already existing not free charges, right? Because it's an insulating material, you don't have free charges. That means all the charges here are bound charges. They are bound towards the center of the nucleus. They are bound towards the nucleus. So what is going to do? This electric field will displace these bound charge from their position. They get just displaced. That means they are being moved from their position by a small amount. That displacement is going to result into negative bound charges over here on the left hand side and positive bound charges on the right hand side. Resultant, what do you get? You get many number of positive bound charges and negative bound charges. All the negative bound charges are close to the parallel plate in which you have positive free charges. All the positive bound charges are close to the negative free charges in the right hand side parallel plate. Now the next, what is going to happen? each of these bound charges, they are going to exist as a pair. So what had happened? You had this electric field due to the free charges because of the applied voltage, that, or the applied potential, that is going to displace the bound charges from their position. So you get many pair of bound charges, positive and negative. Now you can just see that a pair of bound charge is a pair of charge in general, a pair of charge separated by some distance is what is defined as an electric dipole. So basically this displacement of the bound charge within the dielectric has resulted into many number of dipoles. So you get one dipole here on the top, then you have another one, then another, like this you get many number of dipoles. Now just one more point I want to tell here. Because these bound charges have been displaced due to this electric field or the applied potential, that means they have been caused to move by the electric field, right? So we call these bound charges now as induced charges. They have been resulted in the movement of these bound charges have been a resultant of this applied electric field acting on the dielectric material. So you call these negative and positive bound charges as induced charges. So either you call as bound charge or induced charge. So what do we have here? We have many number of dipoles. So obviously when you have a dipole, there also exists an associated electric dipole moment. So how do you define a dipole moment? Very simple. If you remember, mu dipole moment, electric dipole moment mu is given as the charge, the magnitude of the charge multiplied by the distance of separation between the charges. So in our case also you have the bound charges, all different is their polarity, but their magnitude remains the same. So we are going to consider that magnitude of the charge q multiplied by the distance of separation between the bound charges. That gives you the electric dipole moment. Now further, I am going to consider the charge q as area of the material into the surface charge density. Sigma is the surface charge density. I have given a suffix p for a particular reason. I'll just come to that. So surface charge density, if you all remember, it's nothing but charge divided by area. So I can write charge as area into the surface charge density, or A into sigma p. And so dipole moment becomes A into sigma p into the distance of separation. In the next step, I'm just doing a small rearrangement. I bring in sigma p first and keep area into distance together. So sigma p, I can write as sigma p into A into d. Now this area into distance is nothing but the volume of the material. So mu, dipole moment mu, becomes sigma p into volume. That means surface charge density into the volume of the material. Now what we have seen in this figure is you have many number of dipoles being generated due to the displacement of bound charges. Many number of dipoles means many number of dipole moment, or many amount of dipole moment, a large amount of dipole moment. So n number of dipoles will result into, yes, n times the dipole moment. So that means I'll get n into mu. N, electric dipole moment is mu, so n into mu becomes the total dipole moment within this material. Now if I consider the total dipole moment over the unit volume of the material, then I can define it as intensity of polarization, or polarization with given by the letter P. So total dipole moment divided by unit volume becomes polarization. So what happens to our expression here? So we had got dipole moment as sigma p into V. Now if I find polarization, that means dipole moment divided by volume, sigma p into volume, surface charge density into volume by volume results into sigma p. Volume and volume get cancelled, so it becomes sigma p. That means polarization becomes equal to the surface charge density. Now this surface charge density is that representing to the bound charges. So sigma p is nothing but surface charge density of the bound charges. Now this entire effect, that means you had a free charge carriers due to the applied potential just on the parallel plates of the capacitor. The applied potential resulted into an electric field. Electric field causes displacement of bound charges. So you got many number of bound charges here. Just think about the total charge carriers. What happened? Total charge carriers become the sum of the free charges from the plates of the capacitor and the new bound charges. That means the total charge increases. So total charge increases means capacitance also increases, because we just remember this, Q is equal to C into V. Now, so this entire process in which we generated so many number of dipoles is called as polarization or dielectric polarization. So the surface charge density sigma p is actually representing the surface charge density of the bound charges, or the surface charge density due to the dielectric polarization, or surface charge density due to polarization. So I give it as sigma p. That means polarization becomes equal to the surface charge density of the bound charges, or surface charge density of the bound charges due to the effect of dielectric polarization. Obviously, I have already defined another way. Polarization is equal to surface charge density of bound charges or induced charges. Remember, this is another name which we have already given for the bound charges. So this particular session we have basically understood what is dielectric polarization, or how dielectric polarization occurs in a dielectric material. And one more point, that inserting a dielectric increases the amount of charge carriers and hence the value of capacitance. So just to remember something here, so if I know the capacitance value when the dielectric medium is there, and the capacitance value when there is no dielectric, that it is air in between. If I take a ratio between that is, say I define C as the capacitance when there is a dielectric, C naught as the capacitance when there is air in between the plates, then I can write as C as epsilon A divided by D, and C naught is epsilon naught A divided by D. Resultant is epsilon divided by epsilon naught. So what are they? Epsilon naught is the permittivity of free space. Epsilon is the permittivity of the dielectric. The ratio what we are getting, epsilon divided by epsilon naught, is nothing but the dielectric constant, or another term, relative permittivity. We call it as relative permittivity. So we during this entire unit of dielectrics, we will be referring to the representation of epsilon r for dielectric constant, or the relative permittivity. In this session, we move on further with the unit of dielectrics. So we just go first into the classification of dielectrics. So dielectrics are basically classified as polar dielectrics or non-polar dielectrics. So what does it mean? So a polar dielectric will always have the center of the positive and negative charges separated by a small distance. So if I consider two charges, positive and negative charges, then their center will be always separated by some distance. So we say that means since the charges are already separated, you can call this as that they already have dipole moment, or in another term we can say that they possess permanent electric dipole moment. So one more point to be noted is that in polar dielectrics, when there is no external field, these dipoles will be oriented very randomly, and there will not be any dipole moment for the material. When you apply an external field, the dipoles will orient, they will rotate, and result the electric dipole moment will increase. Now coming on to non-polar dielectrics, that's the second classification. Here the charges, the positive and the negative charges, they will coincide, their center will coincide. That means there is no permanent dipole moment. Whenever I apply an electric field, these charges will get separated and they get dipole moment. You call this as induced dipole moment. Now we are moving next to do a small derivation. So let me just go up here. So before that, we need to remember something, that's the Gauss law for electrostatics. So if you all remember, the Gauss law says that total flux in the material, that is phi, is given by the charge Q divided by permittivity of free space. Flux phi is Q divided by epsilon naught. What is flux? What do you understand as flux? It's nothing but the total amount of electric field moving in the material. So if I find integral of the electric field over the surface of the material, then I get the total flux phi. So instead of phi, I am now going to write as integral electric field E dot ds. So it's a dot product here. E dot ds. ds is the surface element, surface area of the material, or a small surface element. So you will get it as integral E dot ds is Q by epsilon naught. That's another representation for the Gauss law. Suppose the electric field being applied is a constant value, then I can take out E outside the integral. So it becomes E into integral ds is Q by epsilon naught. If integral ds I denote as the total area of the material A, then I can write E into A is Q by epsilon naught, or E becomes Q divided by epsilon naught into A. Now this is the form of expression for Gauss law which we are going to make use of to do a small derivation. Let's go back to the notes. So what I am going to consider is, I have this dielectric where at first the parallel plates of the capacitor had free charges, and within the dielectric you have the bound charges or the induced charges. And one thing to be noticed, obviously I guess that you have seen this in the previous video itself, that the bound charges are of opposite polarity with respect to the free charge. So when I try to find the total electric field or the resultant electric field, then I should basically consider the electric field because of the free charges and that due to the bound charges. Now, due to the free charge, say I consider free charges as Q, and for the bound charge, you know that bound charges are of the opposite polarity, so the electric field will be a negative value. So free charges I will consider as Q and bound charges as Q prime. Now let me go further into the derivation. So what do I get? I get the resultant electric field as a field due to the free charges, that is Q divided by epsilon naught A. From where is it coming? It's coming from the Gauss law we just talked about. And minus Q prime by epsilon naught A, again applying the Gauss law, but this time for the bound charges or the induced charges. So Q by epsilon naught A minus Q prime by epsilon naught A. Now Q prime by A is nothing but the charges, bound charges, magnitude of bound charge divided by the area of the material. What is that? That's nothing but the surface charge density of the bound charge or the induced charge. And in the previous session we have seen that this is equal to the polarization P. Sigma P was equal to P. So instead of Q prime by epsilon naught A, I am going to write as P. The next step, I am also doing one rearrangement. I bring this Q by epsilon naught A to the left hand side and take E towards the right hand side. Or in another way, I can bring Q by epsilon naught A on the left hand side and Q prime by epsilon naught A to the right hand side. It's just a basic rearrangement. So the resultant is, I get Q by epsilon naught A is E plus Q prime by epsilon naught A. And Q prime by A was sigma P was P, so it becomes E plus P divided by epsilon naught. So I get Q by epsilon naught A is E plus P divided by epsilon naught. Now what I'm going to do next is I'm going to multiply by epsilon naught throughout. So it becomes Q by A is epsilon naught E plus P. So if I multiply by epsilon naught over here, the epsilon naught gets cancelled. Over here, it becomes epsilon naught into E. And for the second term, the epsilon naught again gets cancelled. So it becomes Q by A is equal to epsilon naught E plus P. Now what is Q by A? Exactly like how we defined here. Q by A is the surface charge density for free charges. Q is the free charge. So Q by A is the surface charge density for free charges. So I'll once again get it as sigma D. I'm going to put it as not P, it's sigma D. That is equal to a term called as capital D, that is electric displacement. So electric displacement is what is Q divided by A, D. Now, so the relation becomes, instead of Q by A, I'm going to put as D. So exactly similar to how we had Q prime by A as sigma P, which was found to be equal to the polarization P. So what was it? Q prime by A was a surface charge density, and when you estimated the polarization, there was a net dipole moment per unit volume. That was for induced charges. If I try to find the net dipole moment by unit volume for free charges, I will get the surface charge density of free charges as same as the sigma. That means sigma D, that is the surface charge density of free charges, will be equal to a particular factor called as electric displacement. So electric displacement is referring to the surface charge density of free charges or the net dipole moment due to the free charges in unit volume of the material. So if I just substitute this back over here, it becomes D is equal to epsilon naught E plus P. This is a very important relation. So D is the electric displacement, epsilon naught is the absolute value, the permittivity of the free space, E is the electric field, and P is the polarization due to the bound charges. Now one point to be noted, D is acting only on the free charges, P is acting only on the bound charges, and electric field E acts on both free charges and bound charges. So this is known as a three-field vector relations. So all these are vector components. So D electric displacement vector D is equal to epsilon naught into vector E plus vector P. So very important relation. Now what I'm going to do next is I'm going to give a definition for P in terms of the electric field E. So you can see here that the polarization P is proportional to the electric field, the intensity of the electric field. So P is proportional to E, and if I try to find the proportionality constants, it becomes P is equal to chi into epsilon naught into E. Epsilon naught is obviously the permittivity of free space. Chi is known as dielectric susceptibility. It's a dielectric susceptibility. Please don't get confused with the magnetic susceptibility, which you would have seen long ago in your 12th standard. So we get the relation between polarization and electric field as P is equal to chi epsilon naught into E. It's a very important relation. So coming down further, what I am going to do is, now I substitute that expression for P, that is chi epsilon naught E, into this relation. So we have just derived D is equal to epsilon naught E plus P. I am going to put P as chi epsilon naught E. So if I do that, I get D is equal to epsilon naught E plus chi epsilon naught E. Epsilon naught E is a constant, so I can take it out, and 1 plus chi becomes inside the bracket. Now this 1 plus chi is given as epsilon r. So it becomes epsilon r epsilon naught into E. What is epsilon r? It's the dielectric constant or relative permittivity. So if you remember, epsilon r was epsilon by epsilon naught. So this entire relation now becomes epsilon into E. So you have another form for the displacement vector, that is D is epsilon r epsilon naught into E, or it is epsilon into E. So, and you also got one more relation here, that is 1 plus chi we are considered as epsilon r. Now I can even rewrite the expression for polarization. So what I have done is I consider P is chi epsilon naught E. That is a relation which we already have. So we have epsilon r is 1 plus chi. So chi becomes epsilon r minus 1. So polarization P can be given as epsilon r minus 1 into epsilon naught into E. Alright, so we just got two expressions. D is epsilon naught E plus P, and we also got D is epsilon naught epsilon r into E. So if I substitute that here into this particular expression of epsilon naught E plus P, so it becomes epsilon naught epsilon r E is epsilon naught E plus P, or P is epsilon naught into epsilon r minus 1 into E. So another way to prove that polarization is directly proportional to the electric field E. So P is epsilon naught chi into E. So one way we also can say that chi is epsilon r minus 1. So we have come across a few relations in this particular session. First one was obviously we started with the Gauss law. So that was electric field is Q divided by epsilon naught A, and then we derived this relation between the three field vectors, that is the displacement vector D is epsilon naught, that is a permittivity of free space, into electric field plus polarization. Now we also get that the displacement vector is epsilon naught epsilon r into the electric field E, and we also get polarization as epsilon naught into epsilon r minus 1 into E. All these are very important relations. And one more thing to be noticed, epsilon r minus 1 is equal to chi, that is the dielectric susceptibility of the material. Now, so one more term to be defined, which before we go into the next session, that's something called as polarizability or alpha. So the dipole moment which the bound charges get when you apply the electric field, that will be proportional to the electric field value. So if I remove the proportionality constant, I get that constant as alpha. So dipole moment is proportionality constant alpha into E. This proportionality constant is known as the polarizability of the atom. So if I want the polarization, total polarization, you all remember that total polarization is how many dipoles are there into the dipole moment, each dipole moment, that means the net dipole moment. So polarization will be n number of dipoles into the dipole moment mu. So that means n number of dipoles into alpha into E. So we'll be using these expressions further in the next session.